before we get into this federated learning, I just want to say a few things about it. So yeah, this is me. I'm currently working as a machine learning engineer. I also do a little bit of podcast hosting, and yeah, I like to share things that I know with the community. So I do share a little bit here and there based on the requirement and based on the topic that I'm familiar with. So currently, I'm doing Masters of Computing in AI at National University of Singapore. So previously, I was graduated from University of Glasgow. I'm doing honors degree in computer science as well. So yeah, I'm pretty much deeper into the IT area, I would say, than traditional, machine learning people tends to have more mathematic background rather than CS. So yeah, this is taking a point of view from a CS person rather. And this is how I started my career. Around 2016, I started working as a research engineer in A-Star, and then I moved over to becoming a software engineer sort of thing. And I'm working for the software development department for about a year. So after that, the AI became popular, and then I want to get on board into the new technologies, and I'm also excited about the new things that we are going to do, we are going to learn. So I joined to AI Singapore, which is the governing body for the AI here in Singapore. So they do a lot of courses, and they do also have programs for you to attend to become an AI engineer. And after I have learned my skills and craft, I move on to test out my skill in the real world. So I decided to join NE Digital. So whoever not from Singapore, so NE Digital is like a digital wings for NTUC, National Trade Congress, and we are sort of responsible for developing digital solution for all the others entities in the NTUC campus. So I'm working as a machine learning engineer over there, and it's been a very good journey so far. Since 2019, it's already 2021. I'm still there, so it's a very good journey that I've been going through. So just a little bit of disclaimer before I move over to the slides, right? So the presentation that I'm going to do is only for educational purpose only, and it's not going to make you how do I say this, a specialist in federated learning, or it's not going to give you necessary skills to conduct a workshop yourself, right? And whatever I have going to mention here is that it's entirely based on my opinions and my learning rather than standard textbook sort of thing. So yeah, so don't take a lot of things that I'm going to say as a textbook, and please feel free to research the material that I'm going to provide. So I do provide a lot of resources that I learn from, so you could also learn from it and also be more proficient than I am. And if I do any mistakes, or if I mention something that is wrong in your opinion, please feel free to contact me. I'm more than happy to discuss with you. And if I need to do any correction, I will do it. So no worry at all. And at any point in time, if you need any clarification, any questions, please feel free to comment, and I will try my best to give you an answer. Even if I can't, I will try to email you afterwards, right? So no worry. So yep, and the slides encompass a lot of images and videos and the content. So I didn't create any of this, right? Because I'm not an active federated learning researcher. So what I did is I just try to consolidate things that I learned when I was doing for my day-to-day work. So I just want to make it available for everyone. Things that I learned, things that I gathered, so make them into one deck so that I could easily share to everyone. But I do not own any of the contents over here, just to be clear. So yep, without further ado, let's get deeper into the content. So I'm not sure how many of you guys are familiar with data science. So data science, in my opinion, is about extracting insight from your data, and then you use them to solve the problems across the domain, right? So a lot of people talk about data science being just building models, or just trying to do analysis, but data science is actually much more than just building a machine learning model, right? It's all about extracting insight and try to use them to your advantage. So without using those insights that you get from the exploratory analysis or the prediction value that you get from the model, and there's no point doing any data science stuff, because if you're not going to use it, what's the point of doing it anyway? So if you are familiar with it, you will know data science actually, standard data science like machine learning, is going to work like this, right? So you have a particular group A, group B, group C from the right side. So you have a lot of data from a different entity, and you try to gather them into a one trusted party. It can be your own environment. It can be your own organization. Just consolidating everything. You just train on it, and then you produce a final model. Right, that's typical standard machine learning works. You collect your data, you train it, you clean it, then you train on top of it, then you get your model. Right. So what's wrong with having this kind of standard model, right? Is that when the new privacy laws or GDPR, PDPA sort of things comes in, and suddenly the entities from different organization can't share certain part of your data anymore. For example, in this photo, right, the group A, you can share certain features out of it. Maybe it can be a person name, a person phone number, or their date of birth, or things like that. And group B, they can't share one of the features that you're supposed to use, right? And group C, they can't totally share. It may be because their financial record, hospital records, their health record, they can't totally share with any of the third party anymore. Then what happened to your previous framework, right? You are supposed to gather everything, train it using a third party, right? You're going to consolidate everything and you want to train it on top of it. But without all these features coming in from different entity, you can't really train a final model. So this is actually impact a lot of machine learning models these days. If you are in active space, you probably like try to find a workaround, try to anonymize the data using hashing and things like that. But when is really can't hash anything and you really need to share the data to make it work, then you need to find a way to work around this solution, right? This problem is actually affecting everyone based on the privacy issues. So the researcher were thinking hard, and then they try to say like, oh, if we can't bring the data to us to train the model, how about we bring the model to them to train the data, and then we bring it back just the model, right? So it might works when if you really think about it. If we can't bring the data, how about we bring the model to them? So that actually one of the initiatives that they try to do, just by bringing the model to the individual entity, right? So I don't really need your data to send to me anymore. So what I need to do is I want you to train the model based on the data that you have, and then I just take back all the weights from the model. So it looks simple from the diagram, but there's a lot more thinking and a lot more architecture, a lot more calculation is going to happen at the back end. So I just want to stress that this is actually a very active research area, and a lot of things are changing rapidly. And then if you are following this, right, or whatever I say, it might be outdated maybe 6 months or 1 year from now. Just to bear in mind that things I'm going to say is going to change really fast, right? So this is how they are going to do it. Let's say we are going to try linear regression model. So step one, you have a master model who is going to have just a straight line, that's a slope, right? And it's going to copy out the exact same model that master has to all the branches, right? All the nodes. So from the central server, copy out. From the step two, I'm going to copy out everything the same, right? Then from the step three, they will each use their own data to actually train the model. And obviously, when you train the model used on the data, right, your slope going to change, right? Your weight is going to change. So once your weights are changed, so this is basically just a linear regression model. So you are trying to fit the data, the closest fit, right? If you do high school math, you're probably familiar with this kind of diagram. So once you have it, then you sort of train everything. All your data are actually stay in the entity itself. Then you just get back all your weights into the central server or the model server. Then you average out all the weights, right? Then you get your final model. That's one way to actually train, that you bring a model to the data and then you get back the data, you get back the model that trained on the data to create another model, the final model. So the Ashe actually asking questions regarding the which model to train for any particular problems, right? So I would like to say that there is no fixed rule that which model is good for which sort of problems. It really depends on how you craft the problems, right? Let's say you're going to try classification, like image classification. People would try to suggest that you do k-means, or you try to do any of the classification problems and see which one actually suited for the best, right? And some people will argue that I would try to convert all these things, all the images into a separate domain and try to do a clustering on top of that. Or even like it depends on your problem, right? So if your problem is more for classification, you can try all the classification model and then see which one perform the best for your data set. And also if you are like familiar with deep learning, things like that, you can try building a deep learning model, not just a machine learning model. And also whether you have how many data set you have. If your data set is very low, then you probably have to stick to like transfer learning where the pre-trained models are available. All you have to do is just update the weights based on the data that you have. So it is really depends on how you craft the problems and also what kind of training data set that you have. It's not like, oh, I want to do classification, then I use this model. I want to do regression, I use this model, and yeah, things like that. I hope that clears up your confusion. So there isn't a rules. If someone has a rule, please let me know. I'm going to just write it down in somewhere. It's going to be very helpful for my job. But I haven't came to that rule yet. So yeah, in the audience, if someone has a rule, which model can map to which problem, please let me know. Yeah, I will pay you as well. Yep. Thank you, thank you. Right. So let's moving on to the next steps. So similarly distributed weight. Okay, so there's another question. Is that assumption that local data should be similarly distributed to the weights of the central? Yeah, so I will go through that kind of architecture here as well, because sometimes people like to assume that like you said, different weights or the same weights across every model. So I'm going to do just the normal average. But some people like to do like weighted average, and see it is also another hyperparameter that you have to tune it, right? So when you train the model, you are basically tuning hyperparameter for the specific model. But in this kind of condition, you also have to train hyperparameter in the sense that how many of the nodes I need to take in, right? And how much do I have to wait for each particular node that I want to do? How trustworthy is particular node, right? And depends on whether I want to take it or I want to reject it. Is also another decision you have to make as an architect for this kind of thing, right? So the one that I mentioned just now is just an example, and a lot of things that you need to consider are those kind of things, like whether you assume that all the data is coming in, and even sometimes you might even consider things like invariant classes based on the node. So node 1 may have 5 classes, but node 2 only, and node 2 and 3 only have 2 classes. How do you solve this kind of problem, right? So those things are also your decision, whether you want to just chop it off at 2 classes, or you want to make sure you collect more data for node 2 and node 3 to get more balanced classes. So these kind of things are actually based on the people who create this kind of solution, right? There's no correct rule, I would say. You keep on trying until you get the best result out of it. Yeah. I hope that answered your questions. So yeah, let's move on to the architecture part. I think after this, you probably have more idea on what I means by different architecture and different way to consider. So from what I read, there are 3 types of architecture that you can adopt. So centralized, decentralized, and heterogeneous. I will give you a little bit deeper into what it means in terms of architecture. Right. So architecture, this is a centralized architecture. As I mentioned previously, each model will train on their own respective data, and they will upload their weights to the central server or the central model. Then the central model will then either average it, weighted average it, based on the algorithm that you choose to consolidate it into a final model. Then they will distribute back, right? So this is one of the architecture you can adopt, but the downside is that once the central server goes down, all the others connections are lost. Right? You have a central point, like one point of failure, the single point of failure. Once the server's down, the whole system doesn't work. So that's one of the downside, right? Another downside is that your central server need to be bigger than everyone, right? Because you're going to be communicating with everyone. So if your central server is not strong enough, you might create bottlenecks, right? You can't communicate with all the other nodes as fast enough, or maybe you are causing the delay in the network, things like that. So another way to like solve this kind of like overcome this kind of solution, right, is that people propose decentralized federated learning. So if you are from the networking perspective, or if you are a CS student, you will actually familiar with this kind of diagram, because this is more of how you update things among the network, right? So IoT people, networking people, they should be very familiar with this thing. This thing is that there's no central server in this federated learning approach, where they have each individual cluster or nodes will determine when do they update, and they will talk to everyone in the network, right? So from the left side is actually communicate with everyone, and from the right side is actually communicate with everyone as well. So there's no central point of failure. There's no single point of failure. And the downside of using this is that your network will be overflooded with a lot of communication, right? Everyone want to talk to everyone, and how do you know how much is enough, right? So let's say you have 1,000 devices and you receive 999 devices. Do you wait for one device remaining, or do you just go ahead and update it? Also, you have to set a threshold how much. So yeah, there's some familiar with distributed learning. So distributed learning actually, I think, is that you need to share the data. So like, I haven't been really deep into distributed learning, but if I'm not wrong, distributed learning also want you to share the data. Your model has access to the data, right? Then it's very similar to it, just that this one is sharing the weights rather than the data. So you don't have like the sense of batch from the data that you send it to another GPU to train it, and then you consolidate it back. So there isn't any data transferring happening here. It's only the weights are being transferred. Right. I hope that answer. If you're not satisfied, I could really deep into it and then send you an email. Yep. Okay. So yeah, a lot of concepts that you see here will be very similar to what we have already been doing in day-to-day work, right? Like distributed computing or even edge computing. Some people will say, oh, this is very similar to edge computing. But the thing is, the main point of federated learning is I'm not sharing any data with anyone. So all I share are the weights of my model, and that's it. Yeah, that's the whole difference. That's what I think. Yep. So the next thing is more like, different nodes or different cluster will have different sizes and different features. Then how do you consolidate all these things from making it work? Like usually in IoT devices, different devices will have different capacity, different processing power. So you can't have like very big model going to a small device where they can't even put everything into memory to do inference, things like that. So this heterogeneous federated learning is actually a framework that is proposed by some research group. So I also have a link that you can look into it, and they published a paper about this. This is one of the novel approach that they are trying for different type of cluster and imbalance sort of performance in the local devices, right? If you are very familiar with it or you want to deeper into it, right, you could actually take a look. And if you ask about how the model weights going to update, right, because different devices will produce different weights, and then like the previous assumption that the weights are used on central server equally, or in this kind of heterogeneous framework, they sort of have a weighted sum or weighted average of the weights, right? Because local server, local parameter W1 is contribute a very large amount of weights for the global model, and also like local weight W1 or WL2 is going to contribute maybe about a quarter, and then small ones will only contribute about 1/8 or 1/12. So this is how they decided to use. So the hetero FL is actually a framework. They published a paper. Then you could actually go and take a look how they actually implement it in a ways that is support the heterogeneous federated learning approach. Right. So after we have talked about the architecture stuff, there are different architecture of federated learning, but there are also different type of federated learning, right? So if you're going to think about implementing implementing a machine learning system that going to like not share the data, how do you make sure, right, each individual has a same data set or same features, right? So there's a horizontal federated learning that is from the left side, number A. So client A and client B,
they all have the same features and the target, right? So all they have to do is just train on it, and then all your model probably share the same weights, right? And then they just consolidate them back. So the next thing is the vertical. So the vertical, if you notice from the diagram, client A and client B doesn't share the same features. So A has 1, 2, 3, and B has 4 and 5, but B has the target. So they have to do, what they have to do is they can't just train the model like solely used on the client A. What they have to do is they have to communicate, right? Either each batch or maybe 1,000 epoch, 2,000 epoch, they have to consolidate it back and then try to find whether this particular direction that the client A model is going is correct or not. So if you talk about neural network, right, there will be a backpropagation. So backpropagation is calculated on the central server instead of calculating on the local. I hope that clears up the vertical versus horizontal. Then some people are exploring transfer learning for federated things as well. So federated learning is not just just train the model. There are also people exploring the transfer learning aspect of it. Transfer learning, if you're not aware, is that people really train the model using a lot of data set. Then, or if you want to use it, right, you could salvage some part of the trained model that some people has already trained to suit your need, right? So that's what they were trying to do, right? So the next slides that I have here is how do you do federated transfer learning. So the federated transfer learning in this diagram and the research paper that I link here that you could go deep down and see that there's data from A that is being trained on using the normal federated learning, and then if you want to transfer some of the model, there are some overlap here that you can leverage on, and then you train entire set of data set from B using their new features or things like that, and then you could just use that label and data set from B to boost up or speed up your training using the data set that you train from A. So this is like the federated transfer learning. This is pretty new. So if you want to know more, you could actually follow the research that's happening, and different people will implement different way. And it's a very exciting time to be alive now that everything happen online, and you also can see everything that's happening in a real life sort of approach, right? So after I have talked about all the architecture and also the type of machine learning, I want to give you one use case example that actually Google has done. So if you're following Google sort of Google blog or Google News, you could come across this kind of announcement that they are using federated learning for their Gboard on Android. So things that you type to your friends are not being transferred over to their server. I think I used it to train the recommendation model that is used for recommending places. Right. So how they architecture it is like this. So it starts from the top, which is here. You have a central model that is being distributed to everyone, which is all the Android phones, right? And each Android phone user will use, depending on their personalized content or their personalized usage, the model will change, right? Because they train on the model of the data or the user data. It will change to whatever type here, and then each individual user will have their own model trained on their personalized data, right? So all the personalized data will be stay in the device, but the weights that in train will transfer back to their server. As you can see, different user will have different sort of model produced. Can see from all the shape here, rectangle, diamond shape, star shape, etc. And then it will be sent back to the cloud. So only the weights of the model will be sent back, and then it will do some processing, be it weighted average or weighted sums or more advanced algorithm. And then they will have a new model that is generalized across all the user. Then it will then send it back to the distribute back to all the users again, right? So after that, the user will use again, train again, come back again, and the circle repeats and repeats, right? So the questions now here is that what if there only is one or two user, right? And you are sending back one or two data, and you're only learning from one or two data, and then you send back one or two model. Isn't it the same as just using the data to train the model? So Google impose some of the limits, right? If the user is below some threshold, they don't bother with updating, so that people can't identify like individuality of the model. So you can't associate this model come from this person, right? That's what they told in the blog. So I think they probably do a lot more than what I'm just simply explaining, but to prevent the privacy from the user. Yeah, this is how they implement it. I hope that is clears up. If not, we could discuss it later on, right? So yeah, so the benefits of using this kind of approach is that it doesn't require data to be uploaded across everywhere, and it provides more privacy because the data never move out of the system, or is move out the weights of the model, right? And it's suitable for environments like the hospital, right? So and government's institution where the privacy is really, really strict and the data leaks are really, really serious. And it also makes the real-time prediction possible because your models is actually with the device, right? So in typical machine learning stuff, you will be sending back the data or the input back to the server, and the server will infer it, send it back the result. So there's always a lag time from transferring to the devices to the central server. But in this case, the model resides on your device. So they could do a lot faster prediction, and at the expense of, you have to set up all the architecture and make sure everything works smoothly. And bear in mind that there's nothing limiting from the aspect of privacy, but from the accuracy perspective, right? When you try to average out everything, it might not work as intended, right? So there might be two extreme coming, and then you sort of average it out, and they cancel each other, right? So the accuracy might slightly suffer, and depends on the framework that you're using. Some of the model that you use might not support in this kind of environment, but they are always adding new things because this is a very new field that people are trying to work on it, right? So just wait for a while, and hopefully, a lot of models are available there for you to try out. So yeah, if you are interested to find out, TensorFlow has a TensorFlow federated version. So if you're familiar with TensorFlow, a lot of things should be very familiar to you. And yeah, I actually added a tutorial link. Yep, tutorial link here, tensorflow.org federated tutorial. So if you want to learn more, just like the one that we actually went through, if you're new to this TensorFlow, there's a lot of tutorial, try to classify the digits and stuff like that. So if you want to do more about TensorFlow federated learning, you could actually explore this tutorial, and they could explain, I think, a lot clearer and better than I could ever do, right? So, and if you are worried about the code stuff, this is actually one of the sample code that TensorFlow federated has provided. It's the complete code that you could run it using a Twee client. So the code, in terms of code-wise, it's not so much, right? It's just architecture behind it. Right, so don't have to worry so much about the coding. Yeah, so if you want to explore other framework, right, there's also a framework like Ceph and Fate. I'm just trying to filter out the best one, or I could say the most popular one that people voted online, but there's tons of popular framework open source available currently using be it Apache or be it C++ library. There's a lot of other things, right? Even if you don't want to start with Python, there's also other library that support different languages as well, right? So that's pretty much. So these are all the resources that I have went through. So if you want to read more, deep dive to it, you could also go into these individual links and find out, right? Yeah, there's a lot more resources that I provided here. And if you want to keep in touch, try to ask me questions, try to discuss things, you could always email me, try to find me on LinkedIn just by scanning the QR code over here. It should bring me to my LinkedIn profile. Then you could add in. I'm quite active there, so I could reply whatever inquiries that you have. And if you want to learn more about these kind of contents, I also have a podcast session. So I co-host this podcast with one of the Data Science SG, Data Science Singapore co-founder, Koo, if you know him. Yeah, I also do podcast co-hosting with Koo, It's called Symbolic Connection Podcast. You could find us on Telegram. You could find us on Spotify, Apple Podcasts, and Anchor. Right, a lot of the mainstream platform we are already there. Yep. So yep. Just one more thing before I go. As you know, my whole country now is being traumatized by a lot of terrorist organization. I would say it used to be military, but they are trying to instill fear into the people so that their regime works. So the kids over there has been really traumatized because this tribe is actually a Christian tribe. If anything happened to them, they actually go into the church because that's where they think is safe. But when they go inside, the military shoot the church. As you can see from the left side, there's a hole in it, right? It's a very irony because this means actually peace church, something like that. But yeah, they've been shot down inside the church. Imagine how frightened they might be. And yeah, if you want to help these kind of unfortunate kids, right? They are trying to, yeah, there are a lot of GoFundMe things here over there, and you could try this link. And if you want to individually contribute in a more capacity, you could also talk to me, and I can link you up with the volunteer over there to do more things about it. Yeah.